Assalamu alaikum. In last lectures we talked about mathematical modeling of mechanical systems. We take one more example to practice the concepts. We have this mechanical system and we want to obtain its mathematical model. The system consists of a frame of mass m1. Inside this frame there is another mass m2 which is connected to this frame through this spring, viscous damper on this side and viscous damper and spring on this side. This motion of this object inside this frame is frictionless, that is, there is no friction between this mass and this frame. This overall setup is moving on a fixed surface, and again we assume that this surface is frictionless and there is no friction between this frame and this fixed surface. As you remember, to obtain the mathematical model for this system, the first step is to identify linearly independent displacements. So since this frame can move, so this has certain displacement, and let's name it as x1 of t. To this frame, this spring is connected, and this side of the spring is fixed with this frame, so the displacement of this side of the spring is the same as that of the frame, that is x1 of t. Likewise, this side of the damper is fixed with this structure, and the displacement of this end is x1. The other sides of this spring and of this damper, these are connected to this mass, and this end can have a different displacement from the displacement of this structure, so let's name the displacement as x2. This end have displacement x2. This mass also has displacement x2. Since this is a rigid mass, so this side and this side both have the same displacement, and that is x2. To this side of this mass, a damper is connected. This end of the damper has the same displacement x2. However, this end of the damper can have a displacement different from x2, so let's name it as x3. So the spring, one side is connected here, so it has displacement x3, and this side has the same displacement as this structure. So we have identified the linearly independent displacements in this mechanical system, and we want to have its mathematical model. We shall apply the shortcut that we have studied, that is x1 of s. We are working in Laplace domain, so everything is in Laplace domain. x1 of s multiplied by sum of the impedances which are connected with this displacement. So if we look at this displacement x1, which is the displacement of this structure, what are the impedances connected with it? The impedances are the impedance of this mass, that is m1 s square, in this case 8 s square. The other impedance connected to this displacement is the impedance of this mechanical impedance of this viscous damper, which is 4s, 4 multiplied by s. Another impedance which is connected to this displacement is the impedance of this spring, which is 1, and another impedance, this spring is also, this end also has the same displacement x1, so this spring is also connected with this displacement x1. So one plus 15, so we have 16. So this is the sum of impedances connected with this displacement. The second term is x2 of s multiplied by sum of the impedances which are connected to both the displacement x1 and the displacement x2. If we look at this figure, this structure has this displacement x1, this mass has displacement x2. So what are the impedances which are connected to both of these displacement? So these are the impedance of this viscous damper and impedance of this spring, which will appear over here. That is 4s plus 1. The third term is x3 of s multiplied by sum of the impedances which are common between displacement x1 and x3. So what are those impedances? This spring is connected to both the displacement x1 and x3. So we shall have here the sum of impedances which are common between displacement x1 and x3, which is 15 in this case. The right hand side of this equation will be sum of the forces, external forces, which are directly applied to this structure, which in this case is 0. For the second equation, we have x2 of s multiplied by sum of the impedances which are connected to displacement x2. What are the impedances which are connected with this displacement? The impedance of this mass, which is m2s square, that is 3s square. This impedance is connected with this displacement. Also this impedance is connected with this displacement x2. So 16 plus 4 is 20s. Next, this spring is connected with the displacement x2, and what else? So here is a typo. It must be 1 over here because this impedance of this spring is 1. So make this correction. Then x1 with a negative sign multiplied by sum of the impedances which are common between x1 and x2. So these two impedances are common between displacement x2 and x1. That is, one end of these impedances is connected to displacement x2 and the other ends have displacement x1. So these are written over here, 4s plus 1 minus another term x3 multiplied by sum of impedances which are connected to displacements x2 and x3. So this impedance is one end is connected to x2, the other end is connected to x3. So this impedance is common between the two displacements, and impedance of this viscous damper is 16 multiplied by s. And on the right hand side we have sum of the forces which are applied to this displacement, which is over here, and written in Laplace domain we have f of s. In the third equation we have x3 multiplied by sum of impedances which are connected to this displacement. That is, here is displacement x3, and here is one impedance which is connected with this displacement, and another impedance which is connected with this displacement. So 16s plus 15. X2 multiplied by a negative sign and sum of the impedances which are common between x2 and x3, that is, which are connected with both x2 and x3. So this impedance, one end is connected to x3, the other end is connected with x2. So this impedance is common between the two displacements, that is written over here. x1 multiplied by a negative sign and sum of the impedances which are common between x1 and x3. So the only impedance which is common between displacement of this structure, that is x1 and x3, is this spring, and impedance of the spring is written over here. So these three equations describe the mathematical model of this mechanical system. We can obtain the transfer function for this mechanical system. These here are the three equations which were written on the previous slide. We can write these equations in matrix form like this one. So if you multiply this matrix with this vector, again you get the same equation, that is this term multiplied by x1 and this term multiplied by x2 over here, and this term multiplied by x3 which is written over here, and the right hand side of the equation is 0. Likewise, other equations are entered in matrix form over here. We are interested in obtaining a transfer function between displacement x3 and the applied force f of s. For that purpose, we can apply the Cramer's rule, with which you are well familiar. By the Cramer's rule, x3 of s is obtained by this determinant of this matrix divided by delta. Here this matrix is the same matrix over here, except the third column is replaced with this right hand side of this matrix equation. And this delta, what is delta? Delta is determinant of this matrix. You are well familiar with the this Cramer's rule. If we expand this determinant, we can see that expanding by this third row will be more convenient. So f of s, rather minus f of s multiplied by determinant of this part, which is written over here, divided by delta. Therefore, if we bring this term to the left hand side to find the transfer function, x3 of s over f of s is given by this relation, where again this delta, you know, is the determinant of this matrix. As a homework, you are required to expand these determinants to find the overall transfer function for this particular system.